Good evening. Am I audible to you? Can anyone confirm? So let me start. I think people are less aware. I guess my screen is visible to you. So this is live session number one. I am Pulak Viswas, and this is for the course Numerical Methods, Finite Difference Approach by Professor Ameya Kumar Nayak from the Department of Mathematics, IIT Roorkee. I am PMRF at the Department of Earthquake Engineering, in the same institute, IIT Roorkee. So in this session, I will first try to give a brief summary of whatever uh, topics are covered during the first week, and followed by that, I will solve few problems that I think that will help you in your assignments. So here are a few important facts that actually this course mostly focuses on the ordinary differential equation and partial differential equations, and I guess you already know those things because there are some prerequisites for this course. So I would like to highlight. Please mute yourself. Thank you. So as you know, like for differential equations, in order for this equation to be applicable, there is some domain always specified along with the ODEs, and also some initial and boundary conditions are associated with these differential equations. If you come to the classification of PDEs, so it is like here you can see one generalized linear partial differential equations, considering two variables here, x and y. So it is having this kind of form. These three and other linear first order terms are there. So in order to determine the class of this PDE, what we do, we try to find out the value of this parameter. So you can see B for AC. So if its value is less than 0, so it is classified as elliptic PD. If this value equals exactly equal to 0, then it is called parabolic equation, and if it is greater than 0, then it will be called hyperbolic one. Similarly, suppose now we have three independent variables, x, y, and z. Then this is the equation of the PD. And again, we can determine the class of this PD. For this, we need to construct a matrix like this, where you see all the uh, coefficients are arranged in this form. Now we can calculate the eigenvalue of this specific matrix, and depending on its value, we can say that whether it is elliptic, parabolic, or hyperbolic. So if you find that all the eigenvalues are non-zero and having the same sign, but one of them is having a different sign. So suppose, for example, I'm taking few numerical values. Suppose the eigenvalues are having 1, 1, and -1. So these two are having same magnitude, but one is having opposite sign of the other two. Then it will be called a hyperbolic one. Now we can calculate the determinant value or the eigenvalue. So if the determinant becomes 0, then it will be called a parabolic one. And if suppose one eigenvalue is 0, then it will be again called a parabolic one. And if all the eigenvalues are non-zero and having the same sign, suppose 1, 1, and 1, then it will be called elliptic. And there are few standard forms of PDEs of different classes. Like for elliptic classes, we generally consider Laplace's equation and Poisson's equation. For parabolic case, the most important one is the heat equation. It is having a time differentiation and a second order spatial differentiation of the primary variable u. And common example of the hyperbolic equation is the wave equation, where we have second order derivatives of the problem parameter u with respect to time and space both. Now, as I said in the first slide, initial discussion, that along with differential equation, some boundary condition and initial conditions should be provided. So here we are highlighting the boundary conditions. So boundary conditions are few constants that are provided at the boundaries of the problem domain. And there are mainly 5 types of boundary conditions. And these are Dirichlet, Neumann, mixed, Robin, and Cauchy. For Dirichlet type boundary condition, the boundary condition is actually specified in terms of the problem parameters value at the boundary. So suppose these are the equation. This is the equation. So for Dirichlet type boundary condition, the value would be provided in terms of u. But for Neumann boundary condition, Neumann type, the derivatives of the primary variable is specified in order to specify the boundary conditions. And there can be mixed boundary type as well, where the Dirichlet boundary conditions may be specified at one part and the Neumann boundary condition may be specified at the other end of the domain. And these are the other two, like Robin boundary condition and Cauchy boundary condition. For Robin's case, a weighted combination of Dirichlet boundary condition and Neumann boundary condition is applied on the both ends of the boundary. And for Cauchy, simultaneously we apply Dirichlet and Neumann condition at each of the boundaries. So next, going back to the techniques that are needed to solve ODEs. So the first method is the Picard's method. So in this method, suppose one ordinary differential equation is given in this form, where this right hand side function is some functions of the x and y. And as I mentioned that for the applicability of this equation, some domain of applicability should be there. So this is valid for all x starting from x0, and also the initial condition is provided, that is at x0 value uh, the value of y is y0. And this comes the Picard iterative scheme, where for the each iteration's value it is determined like this, starting from the initial condition value, and we will modify these functions where we change the y variables value from the previous iterations value of the y variable. So in this way you can compute the Picard's using Picard's method. You can calculate, you can solve the ODE. uh, and for other methods it is important to know that what is Taylor series and Taylor's theorem. So for Taylor series, it is a technique or a mathematical tool that helps us to find any change in the any variation in the function value. Suppose some function is there fx. Now if it is changes, like some domain is there along x, so if its value is specified at some position x, what will be its value at some other point where x is like x plus h. So if the domain changes by h, then what will be the value of fx that is expressed in terms of the Taylor series. So, and this is the formula, like the function's value at some x plus h small variation from x, it is given in terms of fx, the variation itself h, and it the derivative of the function, original function, and it goes like this. And if we consider terms up to nth term, the zeroth term, first term, second order term, dot 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 nth order term, so after that whatever remaining part is there, that is actually called the error. And this error is having this form. So if we truncate this, in order to work with this Taylor series, in reality we do not consider the entire length of the this Taylor series. Instead we consider only maybe first few terms. So whatever the terms are left, that comes within the error. And this r is specified in terms of other variable xi, and its value is, remember that it comes within x and x plus h. So if you see here the error, look at the error. The error, the what is the order of the error? Order of the error comes as h to the power n. So in this error, if h becomes larger, so the order will be higher. And in order to achieve a better accuracy, so we should reduce the value of this h. And the error is actually represented in this form, like order of how many, like what, h to the power n plus 1 may be the order. So using this Taylor series, we can find the finite difference representation of the derivatives. Like suppose if we consider up to this part only, then fx is the derivative of fx, prime x is the derivative of fx, So if we rearrange this, we can write the derivative as like this, equal to, so in this way the derivative can be approximated. So here are different finite difference operators that are used, the standard ones, like this one. For first order approximation, like if we want to represent the first derivative, then we can either use the forward difference operator or the backward difference operator. Now, if we want to use the second order approximation, we can use the central difference approximation like this, like del phi del x equal to phi x plus delta x minus phi x minus delta x by 2 delta x. Similarly, for the second derivative, we can use the central difference operator like this, one step ahead, one step back from the point of calculation, minus 2 times the function's value at the exact point. Similarly, other higher order derivatives can be calculated. So this is represented for fourth order approximation. This is having this kind of expression. Now the main important thing that comes, like in order to solve ODEs, are the Runge-Kutta schemes. So suppose this is the equation, one ordinary differential equation with the initial condition is given like this: at t equal to 0, y's value is y0, and this is valid for some domain like 0 to t, capital T. Now suppose this derivative, the definition of the derivative, it says that we can write the derivative as the ratio of the differences like delta y over delta t, where this delta t tending to 0 is tending to 0. But as you know, on computers, like we are dealing with numerical methods, so we will be mostly using computers. So on computers we cannot reach up to 0 limit. So infinitesimal and infinity are non-existent for computer languages. So what we can do, like we can still represent this derivative in terms of ratios of the variations in the y and the time. In this case here delta t is like this. So if this delta t is very small, we can actually represent, we can approximately represent this definition in terms of the ratios of differences. So now in this equation, like we have represented this dy dt through this, so this may be approximately equal to this one, like this. So now if we rearrange this equation, we can get the scheme for the Euler's method. Suppose the function's value at some later instant or later spatial position in terms of the present one multiplied by delta t, and this function's value at the present location. And this, if I try to show the grid, it may be like this. Suppose this is the nth value, this is n minus 1, n plus 1, like this. So we can calculate the value at this location using the values at the nth point. So we need the value at nth, delta t is the maybe the separation, and the function's value computed at this position. And this scheme is actually called the Euler's method. Now if you see, like if we can replace this function with some generalized function phi, maybe, then we can reduce the error somehow. Like we are approximating this, so we are approximating this definition. So now if we use some values of f, instead of f if we use some values, some functions, generalized functions, then we can reduce the error. Like you have seen for Fickert's method. If I go back here, you can see instead of this function we are using some modified value of y within fx, within the function. So in a similar way, like if we use some generalized value functions, then we can. And this generalized scheme is actually called Runge-Kutta scheme. Now there are different schemes based on this Runge-Kutta method. One is I already discussed this Euler's method, where this function is exactly equal to the functions, whatever function is there on the right side. The improved Euler method or the modified Euler method. In this case, here we represent in terms of the summation of these two functions. You can write like this: k1, the original function, and this would be k2 actually. This k2 is like this, and then the improved method comes like this: k1 plus k2. K1 is same as the Euler's method, and this is the extra term for the modified Euler case, and we are taking the average of these two values. And again, there may be third order, where we are using three such terms. K1 is same as Euler's method, same as modified Euler method. K2 is again same, and this K3. And here comes the fourth order Runge-Kutta scheme. Here we use four different terms within this on the right hand side, and these terms are having this kind of formula. So as you know, the Euler's method, it is also called first order Runge-Kutta method. So it is actually based on that. That is this generalized. So if it is this is actually determined from Taylor's series. So for Euler's method, it is first order. For improved Euler, or it is also called Hume's method, this is second order Runge-Kutta method, third order, and fourth order. And in these different methods, the errors are defined like this. For this case is actually of the order of h squared. Here for the improved Euler case, it is h to the power 3. Here it is h to the power 4 and h to the power 5. So okay, this was the little bit of summary. There are other topics, those are actually left. And now I will show you some problems that you can also solve along with me, and those will help you, like in order to solve the assignments for week 1 and maybe week 0. So okay, Let me start. And suppose this is a first problem. It says that consider one OD, this dy dt equal to minus 2 t y square. This is the initial condition valid within the interval 0 and 1. So now we have to use Runge-Kutta method of order 4, fourth order, to calculate the value of like y at 0.2. We have to use h as 0.2. So as I have shown that the formula for the Runge-Kutta fourth order method is like this. K1 is having this form, K2 is having this form, similarly K3 and K4. Now whatever is there, let this one is fx equal to minus 2t y square. And if you see the initial condition, like at 0 time y is equal to 1 and h is equal to 0.2. So at 0, 1, these are given. Now we can calculate this k1. So what we will do, it will be like this: 0.2, the h's value multiplied by function. This is minus 2. 2 is actually, this t is actually 0 into y is 1 squared. So that is why it is coming 0. Now for k2, we have the formula 0.2, fx is this one, but here t and y will be modified like this. So minus 2 t, instead of t it will be t plus h by 2. H is 0.2. So this is t, this is y, n plus k1 by 2. K1 is 0. So if you calculate this expression, it is coming k2's value. Again for k3, you have h. Again this function, but this time it is modified like this. Instead of t, it will be t plus h by 2, and instead of y, it will be y plus yn plus k2 by 2. So k3 is like this, coming like this, that again minus 2 in place of t, it is t plus h by 2 into y, y minus this one by 2. So again if you calculate this, this is coming. Again k4, in a similar way, put the value of t as this one and the y as this one. So this one is t plus h, 0 plus tn plus h, and this one is yn plus this one, and this one is this. So if you calculate this like this, it is coming like this. Now you have this formula yn plus 1 by 6 over summation over these things, sum of those values. So k1 plus 2 into k2 plus 2 into k3 plus k4. So these are coming. This one is 0, 2 into k2, 2 into k3 and k4, and this is coming this one. So the correct answer will be this one. So if I go to the next problem, and this is using Euler's method. So if you recall, the Euler's scheme is like this: at the future value equal to present value plus the increment and the function's value at the present value. But here it is like mentioned, initial condition is y2 y of 2 is equal to 1. So tn equal to will be 2, yn is equal to 1 given, and the increment is 0.1. So if we calculate the y's value at the next point after 2, the starting of the interval, actually you have to calculate it. If you see this is actually given for 2.3, so we have to move up to 2.3. So this is simple, like y's value at 2.1, it will be the initial condition, initial value y1 plus h is given 0.1, 0.1 multiplied by the function is this one, the right hand side. So if you put this thing, it is coming like this. Now in order to calculate y's value at 2.32, we will be using y's new value, this one. So instead of yn, now we will be using the modified y. So this one again, the formula is same, this one plus y and 0.1 into this 2, but here the time will also be changed, will be modified. So this becomes 2.1 and this comes here. This is coming for y of 2.2, and in a similar way, like we have to use this y value and this time in order to calculate for the 2.3 value. So yn, for yn it is coming like this, times h times this t into y square. So t becomes 2.2 and y becomes this. So if you calculate the value of this, it is coming like this, 0.568. So this is the answer for this question. Now here comes the third question, that what would be the value of y at 1.5, but we have to use the modified Euler method in order to solve this equation, this ODE. With the initial condition this and the h is 0.1. So for modified Euler's case, this is the scheme, this is the formula. Here we have to calculate k1 and k2 for each of the increments. So k1 is having this form, k2 is having this form, and the initial condition values are this thing, increment function is coming like this. So if I try to compute for the first one, that is y of 1.1, so here it will be 1 plus 1 by 2 of this k1. K1 is 0.1 times the function, means 2xy, 2 into 1 into 1 plus this k2. So this one is coming, this k2's value is coming as 2. So this one is again 0.1 times. Here I will be using these two values, like x's value will be modified as 2 into, this is actually coming like this, 1.1 into y. Instead of y, it will be yn plus k. So y is equal to y is our 1 plus k's value is coming like 2. So what is its value? If we calculate, you can simplify 1 plus 1 by 2. This one is 2, 0.2 plus this one is how much? 0.1 is 2. Yeah, correct. 0.2. So this one will be modified. So can you calculate this? The whole expression, this one. Yeah, try to give me the value. It is coming like this. 1 point, confirm whether I'm right or not. In the same way, you can calculate for the others. Like if it is wrong, correct, then you can again calculate for 1.2. Okay, thank you for confirming. So can you calculate for 1.2? Try. Like if you want to keep the question. And yeah, one more thing. And this session will be uploaded to YouTube. So I'm sharing the channel link, so you can again rewatch this session, and there you will find these questions as well if you want to solve them. So are you calculating its value? for 1.2. So you have computed. Let me check. You have written 1.548. Let me see. I am getting it. How much? 1.714. Am I correct? Can you recheck? So whatsoever. Okay, okay. Yeah. Again, my mistake. This one would be, yeah, 1. So then I think you are correct. Then it is coming to 7. Yeah, this one is correct. Thank you, Dhruv and this Raphael, I guess. Similarly, you can compute for other values like y of 1.3, y of 1.4, and y of 1.5. Then I think you'll find the answer. So you are doing faster and correctly. Can you complete it like up to 1.5? Uh, I guess no, not today. So have you done for at least 1.3's value? Okay. Yes, yes. Okay, good. So you have completed. That's nice. So let me write it here. 924.44, and this one is 3.124. So 3.144 options are these. Maybe slight mistakes you have done. So yeah, you can do it correctly and choose the correct option. I think you can complete this problem. So I'm going to the next problem, fourth problem. So this is the problem. Next. Okay, so maybe like you have considered many terms, so that is why. But like if you trunk it up to only 3 decimal points, then you might end up with these values. Maybe this one, because it is closest to your answer. Maybe this is the right answer. So check it with hand calculation, and maybe you consider up to only maybe third decimal point. So how we can solve this one? Yeah, can you answer like this fourth question? Like we have to discretize this one using central difference scheme for both space and time. Here you see one first order differentiation, two uh, are there with respect to time and x, and this one is second order. So if you try to do it, you can represent it like this, like for maybe the grids are like this. uh, for spatial location, maybe this direction is x, maybe we represent with I. This one will be I plus 1, I minus 1, and for time we may represent in this direction. So this is n, n minus 1, n plus 2, sorry, n plus 1. So for this point, like if we try to discretize this thing, so it will be like dy dt. How we can write partial del u del t equal to maybe, so this is with respect to time. So at the ith position, the central difference formula, what is it? Can you tell me? N plus 1, yeah, minus u ith n minus 1 by 2 into delta t maybe. And for this one, del x2 by what? And this one again, so if you arrange this in order to compute this one, what is coming? Mhm. For second derivative in denominator, only delta x square. Yes. So it will be coming here. And again this one, plus ey minus 1. So what will be the correct option? You can rearrange this thing into, if I try to rearrange this, I think this is correct. So u I plus 1 n, how it is arranged? I plus 1 I minus 1 n. Okay. I think the options are incorrect, or at least the central difference for both space and time is there, but since no n minus 1 term is here on the in the options, like these things, so we have to use the forward difference for this one, or maybe we can do in this way, and whatever is coming, let it come. Option will not match, I guess. That's it. So this one is coming, like if we use central difference for both time and this one space, but if you use the forward difference, then one of the options will be coming correct, I guess. You can try that one, like instead of this central difference for the time derivative, you use this one. Then can you tell me what is the correct option then? And this is easier, simple to substitute and rearrange the things. That's it. Now for this one, you use central difference, and for the time you use this one. Beta is there somewhere. Okay, I missed the beta. So this will be similar as this one, the first term, but this 2 will not be coming. This 2 will not be coming, but this term will be same. And for the second term, since we are having this one extra, so on this side, instead of this term will be there. So 1 will be coming on this side. Without this 4, it will be 2. So if I write it, okay, plus 1, 2 delta x. Yeah, here 1 extra is coming. And for this one, again it will be similar. No square term is there. So option C, I think you are right. What? Yeah, it should be correct because 1t, this 2 is not coming. This, yeah, that 2 is not coming. Yeah, so option C is correct. Okay, so here the question is little incorrect. Once it should write forward difference for time and central difference for the spatial derivative. But if we go with the question, then this is the answer. So can I do this one again? Easier. How we can do this? Now we have to determine this is the finite difference representation for what? For which of these derivatives? How we can do this? How we can solve this problem? Any idea? So here we were doing from the expression we were using the derivatives to go forward. So here we were using the equation and replacing them with the finite difference approximations. Then now we already have this expression. We have to determine for which derivative it was like this. Actually, you can use the Taylor series formula for this. Like in Taylor series, what it says, x plus h equal to maybe x plus h, use derivative, or maybe I write du dx plus h square by 2 d2u dx2, like this. So you can write this in other way as well, like u maybe n plus 1 un plus h, or instead of h let me write delta x so again, or instead of n I should have written I here as well. It will be coming like for I minus 1, this one will be minus, yeah, minus delta x du dx plus delta x square by 2 minus dot 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 for ui. So again, one last is there, ui minus 2. So can you tell me what will be this time? Ui minus, this is since it is 2, so now instead of delta x, yeah, there should be 2 delta x. 2 delta x square means, so if I write directly 2 delta x square, what you are saying? Yeah. So now if we add these things, 2 plus 1 plus 3 ui minus 6 ui minus 1 plus ui minus, we should use Taylor series x for ui minus 2. For ui minus 2 we should use x. Yeah, here only the increment is there, and rest it will be expressed around the x point. That is why I guess. So what it is coming, like if we add up like this, 2 ui plus 2 delta x du dx plus delta x squared, and maybe the rest of the terms. Minus 6, this one. What number of terms do you recommend to write for that type of questions? Yeah, you can add one more term here, because it will not, like, it is up to fourth order, so you can keep one more term here. Now let me see that what is coming, then we can, from this example, we can decide like up to what term we should keep. Uy minus, so if it is there, so what is coming now? 2, 3, 5, 6. This is getting cancelled. No, 0 into uy. For this term, here is coming 8 minus 2, for the next term again 6, whatever next remaining. So now it is divided by 6 delta x. I think I have made one mistake. Yeah, this one is actually minus, so this is again getting cancelled. So in a similar way, I guess rest of the terms will be 0, and when we divide by 6 delta x of this expression, so this is gone. So this is actually for du dx. So this is coming. So my point will be like, since After fourth order is there, you should keep fourth order. You should keep terms after fourth order, fourth derivative. Then whatever will be getting cancelled, it will be getting cancelled. Okay. This is simpler. Can you tell me the answer for this problem? A rectangular grid is there by straight lines like x equal to 0 if it is x, and if this is y. So you are dividing this in the interval of 0.1. So how much coming on this side? How much coming on this that side? 1 point will be extra higher. So if you divide this like this, 11 points are coming on this side, and here it is coming 21. So yeah, 11 times 21. This is the correct answer. Next question. This is also easy. So this is about that Lagrange polynomial. This is a straightforward question. That 2 points are given. The polynomial, what will be the polynomial that passes through this point? What will be the answer? Can I answer this one? No. Okay. So if you like remember the polynomial, and the Lagrange's polynomial is having this kind of form like x minus some point and b between 2 points. Like, it is having this kind of form, the polynomial for different points. Suppose it is starting from 0 to up to maybe n, and 2 points are there in between. One is maybe, suppose this is j, this is m. So the this polynomial's value for mth position, it will be such that it is 1 here and 0 here. Again for the jth location, it will be 1 here and 0 here. And it is having the form like, in this case, y times this polynomial. If I represent this with p, so what will be the, can you guess? Now it is 0 to 1. 2 points are there, 0 and 1 instead of m and j. So for 0 it is like y0. No, actually the reverse case. Yeah, x minus x0, x1 minus x0. So when x's value is x0, then it is 0. So y1, and yeah, the reverse order. And for this value, like x equal to x1, again it is 0, and we are getting what? X1. Yeah, then it is becoming 1, and this is becoming 0. So yeah, option A is correct. Again, similar to the Taylor series problem, solve this one for x equal to xn. At x equal to xn, your domain is starting from 0 to n. So here the value will be the n plus 1th value. And you have to use the forward difference. You were saying 1 plus delta x even plus p plus delta x even plus p, this one. So yeah, let me see. Forward difference, yeah, that is easy. Let me do it. This one is un plus beta. So if you simply rearrange these things, you are coming, actually you are getting this one easy. Let me complete this one. This is constant actually j, so we are not considering the other dimension. This is same at j, so that is why it is j. Beta is constant, so yeah, there should be delta x. So there should be delta x, I guess. Yeah, as well. Maybe the options are incorrect. Yeah, this one should be the answer. This one I have already doing that time. Can you solve this one? Like what will be the type of this PD? I guess you know this one, like this thing, the criteria. Like if its value is less than 1, 0, then it is elliptic, parabolic or hyperbolic. So you can calculate that thing. This one is A, B, C. Yeah, here it is having only two like variables, so you can directly compute using that as well. That b square minus 4ac. For this case, when we are having only two variables x and y, or maybe others. So b square minus 4ac, this one is a. See, if you simplify this one, it is coming like this, and ultimately this expression is coming. So now you can check like whether when it can be greater than 0. Like if this one is 0, but maybe these are not equal, then this one will be positive, some value greater than 0, and this may be 0 0, no problem, no issue with that. So this may be the one case. The other may be this one is itself 0, like x and x equal to y. Then what is coming? Then this is less than equal to 0, x and y is same, but the condition is that these are positive. Then it is coming less than 0, so then it will become elliptic. Other cases may also happen, like both are same but negative. Then again this is becoming positive. So we see the options. There are two cases, and this is the answer is coming. Like some condition is there, otherwise it will not be always hyperbolic. and also for elliptic a specific condition is needed. You can check other in that way as well for the eigenvalue. Yeah, that is all. Maybe I missed the 10th question. Okay, no issue. So, do you have any like doubts? Others you can ask. Yeah, can you tell me like what are the errors? Maybe I could answer, maybe not. Okay, let me share you the YouTube link, and you can also ask in the discussion forum. We can later on answer. I have not uploaded videos, but I will upload this one on this channel. Have you completed the week 0 assignments? I think those are basics things. After that, you have to solve the for the week 1. Is there any deadline for submitting like submission of those assignments? What is that? 8th of February for week 1. This week Wednesday. Okay. Maybe I can write that question. Suppose xy by 2 minus 4 x plus y plus 1 equal to 0. This is the equation. So in which region should lie for the above PD to be hyperbolic? Can we do this one in the same way as the previous one? Try this one. For the condition for hyperbolic, like it should be greater than 0. This one. Okay. B square minus 4ac greater than or equal to 0. For R means, let me write down the options as well. Tell me which option is correct. Yeah, try to again do it. Okay, you have to find the region of y. Or you can try this one later, and again we will be having the next session on the next Sunday, and the remaining things, and along with other things for the week 2 that will be discussed on that session. You can try this one. You can tell me the answer for this one. Okay, so it is almost time, 7:55. Like on the errors, what do you have? Like, what do you? What is your? Yeah, thank you for joining. Yeah, you can copy that link. So in error estimate, like what you are having difficulties. What thing? Finished session means, what do you mean by that? Okay, so this is the first session, live session. First, okay, and that is actually taken by other one. So she will be posting in a different channel. For now, I don't know like where, what is the channel or where that can be found. Maybe in the next day, or you can let me share my email ID. You can write me there. I can share you. Yeah, there was a session, but taken by a different person. Okay, so yeah, that may be due to the network issue. Maybe. So you write me email, or maybe you can ask in the discussion forum. There we can share you the links for this those. Okay. Okay. Thank you. Then we will meet again in next session on Sunday. Thank you all. Bye bye.